Stars are not stationary, they move through space. It can happen that a star gets too close to a black hole and experiences the effects of its intense gravitational field. In the best-case scenario, the star is deformed and then completely destroyed by the black hole's gravitational force. But things could get even worse. Welcome to our channel. How do black holes form? A black hole is born from the death of a massive star. Stars spend most of their existence producing energy in the form of light and heat. But only those with a mass more than 25 times that of the Sun collapse under their own weight at the end of their lives, forming a black hole. The collapse can occur directly or after the star explodes in a supernova, while the central core contracts to become a black hole. In both cases, the collapse is instantaneous. According to calculations, a black hole forms in a time interval ranging from a tenth to half a second. Black holes that form from the collapse of stars are called stellar black holes and have a mass between 3 and 10 times that of the Sun. However, there is another type of black hole, those found at the center of most galaxies. They are called supermassive black holes and can have a mass ranging from 100,000 to tens of billions of times that of the Sun. It is still unclear how supermassive black holes form, but it is believed that they may have reached their current size through the merging of smaller black holes. To make a comparison, if we compared the mass of a stellar black hole to that of the supermassive black hole at the center of our galaxy, Sagittarius A, which has a mass 4.3 million times that of the Sun, it would be like comparing the mass of an apple to that of a Boeing 747. Black holes warp the surrounding space so intensely that even light cannot escape their pull. There is a boundary beyond which nothing can escape from a black hole, called the event horizon. Since black holes capture even light, we cannot see them directly, but we can observe their effects. For example, in a binary system where a star becomes a black hole, the other star continues to orbit an invisible object that still exerts its gravitational force. Or we can detect the presence of a black hole through gravitational waves generated by the merger of two black holes, detected by interferometers on Earth. Another way to observe a black hole is when an unfortunate star passes so close to it that it is destroyed by its gravity, an event that causes a sudden increase in brightness. This type of event, called a tidal disruption event, has been observed on several occasions, especially by pointing telescopes toward the centers of galaxies, where many supermassive black holes reside. When a star approaches a black hole, it may experience a non-uniform gravitational force, with the side closest to the black hole being attracted more strongly than the opposite side, causing the star to stretch. This difference in force is called tidal force. It is similar to the effect the moon has on the Earth, causing tides, but much more intense. Now imagine what a black hole with a mass millions of times that of the Sun could do. If a star approaches a black hole, it could pass by only once, following a parabolic orbit, or encounter it multiple times, describing an elliptical orbit. In the first case, the star might gain enough speed to escape the black hole, but if it gets too close, it will be destroyed before it can escape. If it survives the first encounter, it will lose part of its mass, but might manage to escape permanently. The asymmetric loss of mass might even provide the star with a kinetic boost, saving it from the black hole. But what happens if a star is captured by a black hole and forced to follow an elliptical orbit, passing near its fate multiple times? As the star approaches, it is stretched by the gravitational force, and part of its material is torn away. The star survives, but with an altered structure, especially in its outer layers. During the retreat, the star might recover some of the lost material, but the next encounter with the black hole will be fatal. With each pass, the star loses more and more mass until it is completely destroyed. The remnants form an accretion disk around the black hole, emitting intense bursts of light observable from Earth. The matter falling into the black hole forms a superheated plasma ring called a corona, which emits high-energy X-rays. In some cases, the corona may collapse and be expelled from the poles of the black hole in the form of powerful jets. Tidal disruption events depend greatly on the structure of the star's core. Stars with more massive cores resist better and may survive multiple passes, while those with less massive cores are more easily destroyed. Recently, a study published in the Astrophysical Journal Letters documented a tidal disruption event, AT 2018 FYK, that occurred in a galaxy nearly 900 million light-years away. Scientists, using the XMM Newton telescope, observed a star partially destroyed by a supermassive black hole at the center of that galaxy. This black hole, with a mass of about 50 million solar masses, was observed in a quiescent state before recording a luminous event that lasted about 500 days, likely caused by the destruction of a star. According to the data, it was a star similar to the Sun that was part of a binary system. After this event, a second flare was recorded about 3 years later, suggesting that the star is undergoing a partial tidal disruption event, with close passes every 3 years. If the star is not completely destroyed, the next pass should occur in March 2025, with another increase in brightness. Tidal disruption events have been studied for about 50 years and help us understand how accretion disks form around black holes, allowing scientists to determine their mass. Thanks for watching. Please give us a like to support us and subscribe to the channel.